Norbert. I changed my title very slightly by including also binary products here, and I would like to start by thanking the organizing committee for giving me this opportunity to talk to you all a little bit about metal poor massive binaries and their binary products in the local group. And so we've heard both metal poor and massive stars quite a lot in this conference, but they all have a little bit, I would say, different meanings depending on who you talk to. And so for the purposes of this talk, metal poor refers to anything that's at most 20% solar or sub that. This 20% comes from about the average metallicity of the SMC. So you'll hear me also say sub-SMC metallicity. I just refer to 20% or less solar metallicity. For a massive star, really anything that's higher than 8 solar masses, and as you can see here, they're quite central to a wide variety of astrophysical phenomena, and I'm really interested in understanding their physics to kind of draw connections to all these different aspects of astrophysics. And so obviously, for the purposes of this talk, we'll focus on the compact objects and the gravitational waves. And so at some point in your astronomy education, you maybe learned that a star is born, it lives on the main sequence, it evolved to some flavor of evolved star, maybe it'll go supernovae, or if it's very massive, just directly collapses onto a compact object. But I think as we have seen throughout this conference, it's not that easy, unfortunately. A lot of factors can play a role. And so I would say there's really 6 factors of stellar evolution that shape our path from star all the way to compact object. And so this is a graphic from Hershey et al. And so you can see on the x-axis metallicity and on the y-axis initial mass, and on the plot it shows you what your star with a given initial mass ends up as. And again, I show here the 20% solar metallicity, and perhaps you tell me, well, Maude, if I look here to the left in this low metallicity regime, it doesn't look that different. But I guess lucky for me, mass and metallicity aren't the only 2 aspects that really shape a star and its evolution. We can add another factor, which is rotation, and things start to change already. In addition, and now in this low metallicity regime, changes do happen in what kind of remnant we have just by changing this one factor. We can add another aspect, internal mixing, which I exemplify here with overshooting. And as you change your overshooting parameter in your convective core, you end up with different CO core masses, which then again impact what kind of remnant you form. And then lastly, you can have mass loss, which I think Jörg gave us a really great talk about end-of-life mass loss, and we had some theoretical talks about that yesterday as well. It's quite uncertain at low metallicity, but some of the predictions really suggest that we get into this very low metallicity, low mass loss regime, and so maybe we're retaining more of our mass as we get to the end stage of our life. And so obviously all of these are interrelated and affect one another, and it gets really complicated, and this is all based on theoretical predictions at the moment, because in this true low metallicity regime, we don't have a lot of empirical constraints. And obviously I didn't mention multiplicity, which is kind of what I'll continue talking a little bit about throughout this talk. When we go to the higher metallicity regime, we've seen this plot a couple of times, we're really talking about a really high multiplicity fraction. And what kind of binaries does that include? There's kind of 3 flavors. We have the detached binaries that are only gravitationally interacting with one another. We have semi-detached binaries where one star is transferring mass onto its companion. In this case, it's even forming a little disk. Or you can have stars in contact where they're exchanging both mass and energy. And so particularly maybe interesting for me, I think, are these guys. Again, in the Milky Way and LMC, we think about 70% are in this short period binaries, and of these 70% are expected to interact. But what about low metallicity? And I think uncertainties actually both in the high metallicity and the low metallicity regime lead to uncertainties on how we form, for example, gravitational wave events. We heard a great talk by Tomer on bloom, and so I won't go too much into detail here. I'm just saying that this is currently the benchmark for low metallicity, but beyond kind of our local group, it's not necessarily reflective of true low metallicity environments. And so there is no systematic study of these binaries in the extremely metal poor regime, and I really wish that the next slide is Bloom 2.0, and I give you a sample of 1,000 low metallicity massive stars, but we're not quite there yet. This is because if we look at the field of metal poor massive stars, you can see on the left here the SMC and some of these higher metallicity galaxies for my purposes. About 7 years ago, we didn't really have a sample with anything beyond spectral types for these lowest metallicity massive stars. And we've really put a lot of effort trying to fill in this space over the last couple of years, and are also trying at the same time to solve the problems that stellar physics poses to us in this low metallicity regime that we're also addressing in the SMC. And so again, this is a figure that we've seen a couple of times, so I'm not going to walk all the way through it. But focus rather on these steps here early in the evolution of the binaries, and talk a little bit first about these guys right here. And again, to emphasize at low metallicity, but maybe even at a little bit higher metallicity, a lot of uncertainties really start here. And so some of the leading questions in my science, again, are what is the fraction of metal poor massive star in binaries, especially in interacting binaries, and what are the properties of the metal poor massive binary population? So how do you go about finding metal poor massive binaries? Well, there is a couple of treasure troves nearby for me in our local group, which are these star-forming dwarf galaxies with sub-SMC metallicities. And throughout the talk, I'm going to feature WLM, which is one of my higher metallicity galaxies, roughly at 900 kiloparsec or so. And then my true low metallicity galaxies, which are Leo A with 5% solar metallicity, and Sextans A with about 6% solar metallicity. And I put here the SMC kind of as a reference. You can see the SMC is much closer and has more star formation, which is kind of why it's been the obvious candidate to be our first template for these low metallicity environments. And so therefore, it's observationally expensive to get spectra. How do you approach this in a more effective way? Well, you first go look into the archives, what already exists. And so specifically, I was aiming to try to find eclipsing binary in sub-SMC metallicity. And now none of these surveys were designed for the detection of binaries, but people were studying RL-Iris and Cepheids. And so for short period binary, that's actually not a terrible cadence. I'm also showing here a CMD. I think we've only seen one or two so far, and I'm indicating the main sequence for people who are not used to seeing these types of plots. And the star here is the system I'll talk about, and without the time epoch data, there's really no idea to pick out that this is a binary. It's kind of hiding in a very regular spot for a single star. It is not until you see the multi-epoch photometry that you see there is an eclipse. And so this data is already phase folded, but it was taken over roughly 3 days, and is a great start. What I also realized is that that same patch of WLM was also observed as part of LUVIT, the local ultraviolet and infrared treasury, which got some UV data for this galaxy. And so I'm adding 2 additional points here to constrain my light curves. And lastly, this same patch of the galaxy was also observed as part of an early release science program with JWST. And so this is actually not a multi-epoch program, but instead they took very, very deep photometry of that same patch, so looked at it for 14 hours continuously. And for the brightest stars, you can take each individual exposure and basically construct your light curve. And so again, we have a nice a nice other view of the eclipse. So this is all very nice and well, but it's quite qualitatively, and I keep emphasizing for modeling purposes, we kind of want to get a little bit more concrete and quantitative. And so I've been using Phoebe, which is a really great stellar modeling tool. However, one of the downsides to Phoebe is if you try to sample light curves, it can really go anywhere from a couple of seconds to 20 minutes to generate a set of light curves. And if you try to do any more sophisticated fitting and want to speed that up, it becomes quite computationally expensive. So I basically created a little Phoebe emulator specific for this system so that I could use nested sampling and derive more robust parameters of the light curves. And we fit all light curves simultaneously to obtain the constraints necessary to get the stellar parameters of the system. Oh. The fit looks something like this, where the black line is the median fit to the data, and the colored lines are draws from the random draws from the posterior distribution. You can see that we constrain our eclipse pretty well, and obviously where we don't have data points, the distribution becomes a little bit wider. The data is consistent with 2 hot stars in minimal contact. So what does that mean in this context here? It seems to suggest, or Phoebe seems to suggest in this case, that both stars are just filling their Roche lobe. More major sources of uncertainties here are the lack of this coverage of the secondary dip and also the limited UV data. Especially for these hot stars, increasing the UV coverage would be really helpful. One thing we measured with our light curves, but as you can see here has relatively large error bars, is the mass ratio. And the mass ratio is particularly interesting for a system like this, especially if it is in fact a contact binary, because depending who you ask in the modeling community, all your contact binaries should be kind of clustering around here, or depending on how you choose your pre-main sequence assumption or main sequence initial assumptions on your binary population, you can have a wider spread. The other thing I want to point out here is I drew a line through just the 2 other systems that we know to be kind of in this close binary minimal contact phase, and our star is right around this line as well, but consistent with an error bars of both being semi-detached or in contact. And so from the photometry alone, we don't really have a preference. So you have the photometry. Obviously, we try to get the spectroscopy now. And so actually just this September, went to Keck, night 1. I'm showing you here images of the IFU and KCWI. And maybe for someone who hasn't used KCWI before, these blobs kind of get worse as the night progresses, and they're kind of fuzzy. And so there's 2 reasons. Enemy number 1, clouds that are passing through and kind of obstructing our view. And enemy number 2 is the volcano next door that decided to start fountaining mid-observations. And so I'm not showing any spectra from night 1 because I don't think it's very trustworthy. We actually do see some absorptions that are definitely not stellars. So maybe nothing out of multi-epoch. However, luckily we had a night 2. And so you can see that these blobs start getting a little bit better and more precise. It's also, I think, at this point, the time to tell you that this is not my candidate. This is a random blue supergiant in the foreground. Interesting for a bunch of other reasons, but not what we're actually interested in. It's this blob right here that is our contact binary candidate. It's really useful to have such a bright star at 19th magnitude in your field of view, because then I was actually sure I was looking in the right direction. So what does the spectra look like? This is a stacked spectra from about 6 20-minute observations. And so if we take approximately the temperature here that we have from our photometric fit, the H-beta fit actually doesn't look too bad. I masked out here the emission line, which was also a teeny bit surprising because based on available H-alpha imaging, this is not really in an H2 region. So certainly something to investigate further. However, the stellar spectroscopy people here will tell me, well, H-beta doesn't really tell you much. There's a lot of things that go on in the Balmer lines. And in fact, yeah, when we look at helium-1, something is going awry. But I'm being a little bit misleading here because this has no rotational velocity, just temperature. So we start spinning this star up. What do we get? We get still a pretty good fit in H-beta, and so that's maybe why a spectroscopist would be like, sure, H-beta is fine, but show me some real spectroscopic lines. And so the helium line does a better job, so I'm going to remove the non-rotating model here, and we do get a much better fit with this high V-cyanide. At this point, I don't have RVs to report to you, because it's at this quality of data, which is about a signal-to-noise of 30, maybe 40. These are quite challenging measurements, and so it's still a work in progress. Another thing we did for the star, which I think is actually quite cool, is to say, okay, if I have a grid of mesa evolutionary tracks, is there a single instance where I can map all of my observed parameters to a single point in time? And so these models were run by Jan Henneko for me, and we did about 300 mesa tracks, and we actually found about 3 solutions that work. Again, this is quite speculative, as we've learned this week. Binary modeling is quite complicated, but in this case, it would suggest that the system merges. However, I think it would be quite cool if we can do this for a wider grid than just 300 models. And for example, Poseidon would work pretty well for this, and get some statistical results on what we actually expect this star, or system, sorry, rather, to become. And then as we think back to the puzzle piece that I showed, where we start with 2 binaries and go to gravitational wave events, trying to fill in these puzzle pieces with observations and kind of check against our stellar models. Again, I'm really trying hard to build up a population so that we can do more tests than just single objects. And I've discovered about another 20 or so eclipse and binary candidates that I'm currently working on constraining further. And during the same run, obtain spectra of 2 additional low metallicity binary candidates for which we also have the light curve. And so we're really trying to constrain these as well as possible. Okay, so now I'm going to move on from this first phase where we've survived, I guess, the binary, and go to our first binary products in this chain of events. And so at low metallicity, I'm actually really interested at how binary products could be different than in the higher metallicity environments, and also what the properties of these binary products can tell us about binary evolution at low metallicity. And so for this, I'll show a little film by Ilva, where we have, again, 2 binaries. One is slightly bigger over here than the other one, so it starts evolving first. Mass transfer happened. Don't know if inefficiently or not, but it's transferring all its mass onto a secondary. And this one's spinning up really fastly, and to me, this is even maybe a disk forming right here, if I interpret a little bit. And to the left, we have a hot strip star. And so I'll talk about the guys on the right first. Spectroscopically, a BE star is really just a B-type star with emission lines in its spectra, but in the classical BE star sense, it's actually referring to a star that had spun up so quickly that it started forming a decretion disk. And in the spectra, this shows up as these strong Balmer emission lines. Another thing, maybe if you recall the contact binary spectra I showed before, when we turn on rotation, our helium lines start to disappear. So where all these pink lines are we expect actually the helium-1 lines absorption features, but they seem to be all kind of washed out. And so we've discovered 6 of these in LEO-A, which is about 5% solar metallicity, and unsurprisingly perhaps, they're all spinning quite fast. In fact, if you make some assumptions about their radius and mass, the velocity at which they're spinning is between 0.3 to almost 0.8 of their critical escape velocity. Another thing I want to point out here is that this is on a 10-meter telescope for a full night at R of 2000, which is low resolution. And our signal to noise for our best star is about 60. And so I think a lot of the reasons that the plot that I showed in the beginning is so empty is because it is really challenging and it takes the best telescope to be able to observe these types of stars. The other thing that I find is interesting, which is here not kind of completeness corrected, is that a large fraction of these are actually not near any of the major H2 regions in LEOA. And so it'll be interesting to follow them up to see if we can learn something about their spatial distribution in galaxies and how that actually informs the way they interact with their companion, but also other stars in clusters. The spectra gives us a lot of information, but because we're in a regime where everything is so far away, we are really trying to gain the most information through all the possible pathways. And so here I show a panchromatic photometry sample. So it's again actually star K4 from the previous slide. And basically when you fit a single star SED to these types of, so you can ask yourself, okay, how do I remedy this fit? Well, you can either try and fit in two SEDs, but in this scenario, we kept getting a star that was physically really impossible. And so instead, we decided to kind of fix a star to the UV and try to fill in the rest with a disk. And so I say a disk here because this is actually still a stellar model. We're just using this kind of as a kind of test case and to get some constraint on the temperature of the disk, which is clearly much cooler, but perhaps with more sophisticated models, we could actually also learn something about the disk properties. This behavior actually pops out really nicely in the CMD. So again, I'm indicating where the main sequence is here in purple and where the blue helium core burning sequence is in orange, so like the evolved stars. And you can see that these stars kind of hang out on the main sequence in the UV, but if we go to the optical only CMD, they start to really move towards the evolved stars, despite actually being hot stars. And so this is kind of the disk IR excess manifesting itself. LEOA is not the only low metallicity galaxy we can see this for. Doing the same thing with Sexton-Say, but just coded slightly differently here, we can see that the main sequence population in the UV starts to split up into two sequences here. And so I have a HST program that hopefully this February will get data of really deep H-alpha imaging in order to really get a robust measurement of the BE star fraction, but also of the contamination of BE stars on the blue helium core burning sequence. Since for people that care about star formation history and things like that, they often use these evolved star sequence to constrain their measurements. So this is coming in 2026. And so to me, the obvious next question after all these talks we heard is, well, what are the companions of these BE stars? And so I wish I could say, and now I'll show you a black hole, but we're not really there yet. I'm thinking of ways to get measurements to identify potential companions, but instead I'll just show you about a different star that perhaps could be a companion depending on what flavor you get. And so it's this green star that actually shows a very similar behavior than our BE stars. But if you look at the spectra, it's not quite a BE star. It still has your strong H-alpha emission, but now we also see a new strong emission feature, which is helium-2. So perhaps if you've been following some of the high redshift talks, they're really interested in what sources can produce a large helium-2 emission. And so, not to say that this is necessarily strip stars, from which we've talked, we heard a lot from Ilva about, but if we take one of her models, we see that, okay, maybe we match here in the UV, but we're brighter in the redder wavelengths. You can try to increase the dust, which then matches you in the optical, but we're not hitting the far UV points. You can try to combine different SDDs, and again, right, people who are familiar with this type of work, it is only about 8 data points or so that we're using to constrain quite a lot of information, and so large uncertainties remain on what the true nature of this object is. But what works out quite nicely, actually, is that you can take your strip star and add a disk and even a hot B-type star and still reproduce the observed photometry quite well. And so when we take some of these measurements and put them on a plot with the other strip stars that we know about, then we fall right here where the purple ones are the SMC and LMC strip stars from Ilva's sample, and the cyan points over here are these like poofy strip stars that we've maybe also heard a little bit about throughout this talk from Varsha Ramachandran, and we're kind of right in between that, and depending which way we go on our error bars, consistent with either. So I think really the true nature of this system remains a little bit of a mystery. However, it's a really interesting source that may reveal more information about what happens in this lowest metallicity regime. The other thing I want to point out here is that we do detect some RV variability. However, it's not significant enough to really constrain any orbital motion or so on, and we are trying to get more spectra to perhaps try to constrain that. And so for the last couple of minutes of my talk, I just want to kind of face forward a little bit and kind of what I see as potential futures for increasing our sample and really providing actually a lot of the theorists with a crucial empirical constraints on the things you're modeling. If I had infinite telescope time on Keck, I could easily observe another 500 or so. They're within our reach with our current instruments, so we can do it. It takes some time. I'm really excited about LSST because I think it will help us do this kind of eclipsing identification work at a much larger scale instead of relying on, archival or Lyrae or Cepheid studies. If we were to have a really blue-sensitive state-of-the-art instrument on any of big glass, so whether that's the 10-meter class telescope or even the 30-meter class telescopes, this could really push us out to even further distances and also increase our sample locally to a few thousands of stars. And lastly, I'm an early career scientist. I can dream big for the future. If we were to have HWO, something that is really challenging to do right now is to get UV spectra for a lot of these stars because they are so far away. And so a single star requires about 10 orbits on HST to get a decent signal to noise. I think HWO would be revolutionary in that way, and not just taking us further, but even bringing all these local metal poor stars within our reach in the UV. And I'm going to just leave with kind of my main takeaways and what you've seen in my talk today, and I'm happy to take questions.
Thank you very much, Maude. Before we go on with the questions, I think this clock is not showing the right time. So you confirm that. Okay, great. I thought my phone maybe has a glitch.
What time is it actually?
Oh. Hi, Maude, Cheyenne, Shariat. Wonderful talk. I wonder for the first eclipsing binary candidate you showed, and then you said now you're working on some 20 other eclipsing binary candidates. How do you define an eclipsing binary? Do you look at the light curves and is it visual inspection? Like for that one that you showed that was one of the 20 new it looked like it had an asymmetric eclipse a little bit.
Yeah, so the phase folding for the two I showed are very preliminary, so maybe it is actually two eclipses that I'm phase folding into one here. So the shape of it, I'm a little bit unsure about. To identify these, I have a set of cuts I do to reduce my sample from all the stars in the galaxy to a couple, maybe 100 or so candidates. And then most of it right now is visual inspection to just check, am I seeing that dip in at least two of the light curves that I have?
Have you cross-correlated the Leo A BE stars with the X-ray sources in that galaxy?
I think, okay, I should preface this with Margaret Lazzarini just had a Chandra program that looked at Leo A, and I'm going to chat with her actually in a couple of weeks. So I think her data set will probably be a good test to cross that.
Yeah, there's some data Rosanne Stefano took about 20 years ago, and the positional accuracy won't be as good, but if there's nothing there, you'll know there's nothing there. If there's something there, it might be a chance alignment.
Yeah, I think what we did look into that, at least for the stripped star source, and it seemed kind of not resolved enough to really be able to tell confidently that that was a match. So I think I'm just going to wait for Margaret to show me her new catalog and cross-match that. And especially with the BE stars, I think that's an obvious connection right there.
Yeah, okay.
Kyle Rocha, UC San Diego. Thank you for the exciting work. My question is about this eclipsing binary candidate. It looked like the rotating model spectra looked to be doing a better job. Is the rotational velocity you get consistent with the system being tidally locked?
Yes, but I didn't put that on a slide because, again, to get the rotation rate of the system itself that should match my star, right, I have to make an assumption about now I'm going to say the radius. And so the radius, depending on how I choose it, is, I think, actually from the photometry, the best fit radius would be yielding a V Sinai of 277. And what I showed you was 257, but I didn't want to put this on a slide because I think the radius determination is a little bit challenging. So too early to tell if it's actually truly tidally locked. I think either way, we would actually expect the primary to rotate fast, even if it was not in a contact system, because it's most likely the mass accretor.
Hi, Maude. Amazing talk. Thank you. I have a question about the strip star and its effective temperature. So the dot you had in the HRD, it was sort of in between ILVAS stars and the puffed up ones. And which is very interesting because I think in models, we tend to see that in lower metallicity, maybe even the fully stripped stars are a bit cooler. So I was wondering what is the most sensitive measurement to get the effective temperature and how the helium emission, helium-2 line depends on the temperature.
Yeah, what I didn't show is the UV spectra we have of this star, which is a little bit more sensitive, I think, to these measurements. Maybe I'll just show it. So this is the helium-2 line in the UV. Actually, here it's just showing the variation of mass loss, so I didn't talk too much about other peculiar features of the star, like pretty strong mass loss but slow wind. There's a lot of things happening that I think part of the reason why we've been taking a bit of time to get this out is because we're really not quite sure if this is 100% a strip star, but I don't know if Ilva also wants to weigh in on this.
Yes, indeed, and I think it's really nice the way Maude phrases it, because it's a weird object in several ways. It has helium-2 emission, which would require both hot source that can ionize that material, and we find a well-fitting atmosphere model for about 45,000 Kelvin, but it requires a mass loss, which is very puzzling. So we're working on getting it out, but thoughts in this type of direction is very welcome. Yeah, it's an interesting object.
Hi, Maude. Really nice work and exciting stuff. About the BE stars in Leo A, and I'm sorry if I missed it, I wasn't sure what exactly your sample selection was. You found quite a few of BE stars, and I was wondering if you have any sense of the fraction of BE stars in this galaxy. I think Abel Schrotemeyer didn't actually determine.
Yeah, so actually for Sextans A, I did compare it with Abel's fraction. I think his fraction is bias corrected. My fraction is not. I would say my fraction is a lower limit, and it's roughly around 20-25%. The H alpha imaging, I think, should help us get a little bit more of a robust sense of the fraction, just because some of these stars may not show as strong of an IR excess. For Leo A, the sample selection is actually biased, because what I wanted to do originally is get a very uniform sample of main sequence stars. And so I selected the bluest, hottest stars here, which then ended up being like half of them BE stars. So I think that's the bias a little bit versus like picking them on the main sequence in the optical. I will say I don't have a robust Leo A fraction for the BE stars, in part because of the coverage of the photometry is not quite as complete as it is for Sextans A. I mean, Sextans A is closer to like 80%, versus here we're perhaps at 60% of the galaxy. So I feel a bit more hesitant to put OBE fraction. However, yeah, I was surprised actually, maybe not surprised on that there is a lot of BE stars, but that my spectroscopic sample ended up being large fraction BE stars.
Hey, Maude, will UVEX help? Is it sensitive enough, higher spatial resolution? Will you add more galaxies that way?
So the biggest issue with UVEX is the spatial resolution for a lot of these galaxies. I don't have a plot in this talk, but I did like for Sextans A, one of the like most crowded regions, for example, you'll see that UVEX does a lot better than Galax, for example, but you're still limited to kind of a couple of clumps instead of the individual stars. I think for some of the stars where they're more isolated, which is, I think, roughly perhaps 20% of the massive star population are thought to be like in the field. These are a little bit less crowded. I think for these types of systems, UVEX will be really helpful to actually also perhaps identify hot sources that aren't as bright in the optical.
Does it have a multi-epoch capability? I don't remember.
I think so. I'm looking for some of the UVEX people, but I think it does, yeah.
Oh. Hi, Martina Hrušníčka. You've mentioned that your sample from the Leo P, I think, was offset from H2 regions, most of the stars. Is this a bias against finding them in H2 regions, or is there something more to it?
Again, I think because we didn't spatial, so the bias here a little bit is that for the sample we used the multi-object slit mask. And so the stars we selected inherently couldn't be really close together, so we didn't have a large sample of what is in the H2 regions because of how we have to select the stars in the slit mask. So I think there is perhaps more of these in the H2 regions as well. I mean, 2 of them are near the H2 regions, but we weren't sensitive to them because we picked the brighter O stars in most of the H2 regions.
Okay, I see.
I also have one more question on your presumed contact binary. So from theory, we would expect if we have a detached binary, then the luminosity ratio goes roughly like the mass ratio to the 3rd power. But if you have true contact binary, it's roughly proportional, so power 1. So it's a big effect. Your mass ratio was 0.4. Can you say, is it closer to one or the other?
I think I have a HR diagram, because I need to remember where it is. lots of backup slides. Oh, there we go. Oh, no.
I see no more hands, and time is up anyway, so let's thank Maude and just try again.